All right, and I'm going to just briefly introduce our last speaker of the night, Dr. Timothy Lukis. Dr. Lukis is an assistant professor of neurosurgery, and he's also the director of the Translational Neuromodulation Lab here at Penn. He received his MD from the University of Florida, and he completed his residency in neurosurgery at the University of Washington, where he also earned his PhD in physiology and biophysics. He's also a practicing clinician here at Penn, and he specializes in the surgical treatment of epilepsy and brain tumors, as well as deep brain stimulation for Parkinson's disease and other movement disorders. His lab works to develop new implantable technologies that interact with the nervous system to bypass or augment damaged pathways. Please welcome Dr. Lukis.
How are we doing on the top row? Can you hear me okay? All right, sounds good. So I am a neurosurgeon. Don't worry, I'm not running for office. I also know that I'm the last thing standing between you and an open bar. So I'm going to hurry along tonight. Feel free to interrupt with any questions, of course. So first of all, thank you to the Public Lectureship Committee for inviting us to be here. It is an honor for me just to share the stage with Casey and Danny. Danny and I just recently began some collaborations, and I'm already your #1 fan. So what a pleasure to actually be here with you tonight. I run the lab jointly with Drew Richardson, featured in these photographs. Drew cannot be here due to family obligations, but Drew is an absolutely brilliant scientist, and I hope you all get a chance to know him sometime soon. We study many things in our laboratory, but tonight we're going to focus on sensory motor prosthetics. I'll define what that means in just a few minutes. I have a very long title, Emerging Intersections Between Neuroscience and Engineering, Brain-Computer Interfaces Meet Body Area Networks, but you could abbreviate that as we study cool stuff. We have no financial disclosures. All right. So let's begin with a bit of background. As you all know, dexterous hand movements are a defining feature of human existence. Our interactions with the physical world hinge desperately on our ability to explore and manipulate objects. Indeed, our social interactions are galvanized by touch and feeling. However, a number of conditions rob us of these quintessential human characteristics, things such as amputations, congenitally acquired lesions, degenerative conditions, of course, traumatic spinal cord injury. Now, recent decades have seen the realization of many motor BCIs. BCIs, to tie back into our introduction, that's brain-computer interface. Motor BCIs read brain signals to various degrees, and they actuate some sort of external device. That could be an anthropomorphic arm with various degrees of freedom. That's an efferent system, meaning it's one direction going from the brain to the body, and unfortunately, it only solves half of the problem. It turns out that somatosensory feedback guides all of our motor interactions. You can imagine just anticipated somatosensory feedback will inform how you'll reach out to touch various objects. You would certainly reach down to touch a spiny reptile differently than you would reach down to grab a little piece of Play-Doh that your child's dropped on the floor. Also, the rate with which we manipulate objects critically hinges on how you expect that object to behave in your hands. You would touch water differently than you would strike a piano key, for instance. So our lab is principally focused in giving back to the body that lost somatosensory communication. Just how important is somatosensory communication for motor movements? Just ask someone who's lost it. So there are clinical conditions where people lose selective somatosensation. Here was a patient of mine I saw a number of years ago. He had a lesion in the inferior parietal lobule right next to somatosensory cortex. That lesion caused seizures originating in somatosensory cortex, and we counseled him that curing his seizures and curing his lesion would involve removing that part of his brain and irrevocably change his motor function. He understood that and asked us to move forward, and we did. We mapped his operation, we performed the resection, and preserved the motor cortex and all the cortical spinal descending tracts that you could just appreciate here in red. So he had normal function throughout the awake operation the entire time. We wanted to understand what the effect of that central deafferentation was afterwards. So we followed him clinically for, it turned out to be about a year, but this is up through a third of a year. We mapped his normal function and the affected side. In this task, it's very simple. We gave him a load sensor. It's a little device you squeeze, like imagine a Coke can that you would squeeze. And the load sensor informs a computer screen. As you squeeze the load sensor, the screen goes up and it goes down in a resource meter. The task was just to develop a target force. And once you got to the target force, the trick, the picture goes away. So you have to use just your somatosensory feedback to maintain that grip force. We call that grip force modulation. Just like you or I or this patient's normal side, you can do that task perfectly, even in the absence of vision, just using somatosensory feedback. But forever, after you remove somatosensory feedback, you destabilize the ability to even maintain a grip force. In some instances, he crushes the can. In some instances, he nearly drops it. Somatosensory feedback is critical to inform how we move. How do we solve the problem? Well, we build bidirectional brain, machine, brain interface devices. We call them BMBIs. The whole circuit round trip can be visualized in this strategy slide here. We start with the brain. We work with our partners on testing and developing novel electrode arrays. In this instance, this is a flexible array that you can visualize right through to do simultaneous calcium imaging, if you're interested. You can build, as we have, and patent these little devices, the pen brain-machine brain interface that decodes neural signals, runs onboard computations, and then controls external effectors. Well, not just external effectors like a robotic arm, but also an internal effector, say for instance a paralyzed muscle, by providing electrical stimulation to that dead muscle to make it contract. Or you can control virtual arms, like this computer-controlled arm right here in our implanted patients. The more important part, as I was indicating before, is this limb, the afferent limb, the sensor-brain interface. How do we solve that problem? Say in someone who's got a spinal cord injury and has a perfectly normal motor system, I should say perfectly normal anatomy, normal muscles, fingers, joints, etc., but no communication? Well, we're working to develop implantable or wearable sensors that go underneath the finger skin. These can be battery-powered systems. They can be passive systems, as the ones we're illustrating here. They communicate wirelessly with what we call a body area network, just like you have a network at your house. This network is pinging from a little watch you would wear like an Apple Watch, or here's my Garmin watch. Could even be satellite linked if you want, but that's not this case. That information then gets sent to a novel brain stimulator that can be on the cortex or the brainstem or any number of locations. And that closes the loop. We innovate in all the areas in yellow. So let's start by talking about brain-machine interface and body area networks. I won't get into the details too much aside from whetting your appetite. This was our first system here. It consisted of 3 separate devices that were all linked wirelessly. Could be your iPad, your iPhone, and your iMac, for example. This is our digital signal analyzer. It can read out brain signals of any sort, local field potentials, individual units from the brain. We have sensors that you can wear on the hand. This is a flex sensor. We have stimulators that can stimulate muscles or brain tissue at various capacities. Our system has grown since generation 1. We're at generation 5 now with increased channel counts, increased capacity. This is a very fancy neural stimulator. I'm not going to bore you with the details, but you can see it makes a round trip from the brain to the machine to the body. Now, before we can implant this in a person, you want to be sure that it works in an animal, right? So we start with our little friends here. Our friend has a little backpack, just like my daughter going to school. In the backpack is the brain-machine brain interface, and it's going to stimulate this little guy's brain to give him super rat powers. In this instance, the super rat powers is a 6th sense. We're going to let him find a hidden platform that he can't see, taste, smell, or touch just by proximity. So it's a homing beacon. This is what it looks like from above when the animal is in the little water Morse maze. We've put these little green dots on the screen. The rat can't see this, but there's a submerged platform in there, and he wants to get to it. Oh, hello, little guy. There he is. All right, so we allow the rat to take a little swim. He needs a bath anyway. And we track his swim pattern. We track the time that he's in there. We track his XY coordinates. I'll just cut to the punchline. He doesn't find it, and we rescue him. Now, you turn the brain stimulator on. It's updating the brain with information on how close he is, a homing beacon to that submerged platform. Let's see what he does. Much smarter than my daughter. So, we also need sensors that are going to be able to go under the skin and give us some force sensation. So here we're exploring these little sensors that are designed to be skin-like. You insert right underneath the finger skin. There we are, the little sensors. You have big joints too, not just little joints. So we have an electrogoniometer that can tell us what kind of joint angles are developed across big joints like elbows and knees. We have novel brain stimulators and novel encoding mechanisms. There's a lot of busy stuff going on right here, but suffice to say that we're the first to show that you can have a chronic brainstem implant in animals for up to a year, essentially, and it's safe. That opens a door for us to take it to clinical trials in people eventually. We have novel math, and we try to map this multidimensional sensor space of lots of different fingers, lots of sensory modalities, temporal dynamics, and so on, into a low-dimensional space, which is brain stimulation. You can only deliver current in individual little pulses. As I mentioned, we collaborate with many colleagues to develop flexible and dissolvable electronics. This is an electronics array here. Here's a small version, here's a big version that you implant in the brain, and over time it dissolves away. So you may not want a device that lasts forever. Maybe you just have to rehab with the device for a couple weeks. We can also anticipate movements before you even do it. And the way that we do that is by decoding brain signals in patients that we're implanting for other reasons, like patients with epilepsy, who have a large grid implanted in the brain so we can find where their seizures are hiding. Well, while they're in the hospital getting their seizures mapped, we ask them to do some fun tasks, and John Burke has been great with this. We have a wonderful supportive lab. We have tremendous collaborators. That's the best asset I think Penn has. Jan van der Spiegel, terrific partner in crime. David Isidore, Nader Ingeta, Danny, the rest of the crew goes on and on. Some spectacular students whose pictures I tried to include today. I wanted to conclude with just our first brain-machine brain interface. It looks like this. Unfortunately, the machine did not work very well, and it turns out that this is Drew, of course. Drew's wife, Hannah, already had a patent on this device. So nothing we can do there. I'm happy to take any questions. Otherwise, thank you so much for your time.
Hi, thank you. In the case of this sort of novel sixth sense that you're giving to this mouse,
Yep.
Where are you directing those afferent signals? Are you mapping them onto other sensory cortex, or where are you sending them?
That's exactly right. So we stimulate the barrel cortex in the rodent. So rodents don't have 5 little fingers with nice thumbs that are opposable like you and I do, but they do have an exquisitely sensitive barrel cortex because they have little whiskers that they use to feel the environment. So we use that as our model system, and they learn that very well.
Hi, thank you for your presentation. I just have a quick question on the relevance of your research with haptics research and a lot of artificial intelligence researches. How is it related, and does one research affect the other?
Absolutely. You know, Penn is blessed with a wonderful GRASP lab, and Catherine Kuchenbecker, maybe even in the audience tonight, she's a brilliant, there she is right there, a brilliant haptics investigator. Certainly these two go hand in glove. I mean, no pun by that, but it's certainly true. The two fields inform each other. They're not directly overlapping necessarily, they inform each other. So education and insights that are gained from one can be equally applied to the other. Yeah. Any other questions before the beers begin? No? All right, thank you so much.
Thank you very much. Thank you, Dr. Lucas. And before you all get up, I just want to say thank you very much to the entire Public Lecture Series committee who put this on, especially Dave Reiner and Megan Healy. Give them a round of hand. Very great job. And thank you to everyone coming out tonight and to our speakers, of course. So enjoy the food.